Right. I think we're now recording. Got no idea how this works, so let's hope it does work. Um, so if I share this with you, you should now be able to see beautiful set of PowerPoints. Right. And then the Zoom stuff's in the way. Right. So today we're going to talk about the kind of questions you guys asked last time, which were in regard to black holes and pulsars, and they're going to come up at the end. And then we're going to talk about the photoelectric effect, which I made a kind of very rushed attempt at kind of explaining and describing last time. And this time we're going to go through it pretty slowly, and we're going to talk about some of the kind of really cool uses it has. We talked about atomic clocks before and how they kind of measure the vibration of atoms and how this vibration is linked to the emissions they make. So I guess the first question I should ask before we kind of even get into what is light is what's your understanding of light? Do you guys kind of have you learnt about light already? Maybe about what we think it is, what you can do with it? If you want to whack stuff in the chat, you're welcome to. What are some cool properties of light?
It's dual nature.
Yes. Okay. Nice. And what does that mean? What does its dual nature mean?
It has both particle and wave nature.
Yeah. Nice. Right. And that's pretty cool and pretty groundbreaking because it means that we can kind of treat it both ways, and it can be used in multiple different applications because of this. You've probably seen light already as a transverse wave, and that's what people didn't think it was historically. Historically, light was seen as a kind of collection of particles, and particles moved in straight lines, and these kind of straight lines hit their target, and that was it. They were seen as these kind of like momentumless, energyless particles that just traveled in straight lines. And that makes sense because when you think about the most common applications of light, you think about shadows, maybe you think about lasers. Light does travel in straight lines. But light also has these wave-like properties. And some of these wave-like properties are things like diffraction. Diffraction is something that is very common amongst waves. And I tell you what, I haven't actually got any photos of diffraction, but give me 2 seconds. I'll show you what I mean when I talk about diffraction here. Diffraction is, oh, this is perfect. Right, let me show you this. Right, can you now see Safari? I hope so. So this is what we mean by diffraction. This is a kind of typical diffraction that you might see from a wave, and you can think about it as water going through a kind of narrow slit, and as the kind of water goes through, you kind of will start to see it expand in its wavefront. And we could do a whole session on diffraction. Very interesting, and it has lots of uses. But light also diffracts, and if you were to shine light through a narrow slit, you would see this same expansion of wavefront. And when kind of physicists in kind of the old days, a few hundred years ago, maybe longer actually, when they discovered that light could do this, it was quite groundbreaking because it suddenly broke up this idea that light was a particle. We had to rethink the way we treat it. And that is what leads to, and this is dispersion. This is quite cool. It's because of wavelength. But that is what has led to our. Oh, why does it stop every time I switch? That's annoying. Right, you can now see. Hopefully, you see everything. Right, and that's what's led to the idea of photons. And photons are kind of a means by which we can treat light as a particle. But when we talk about photons, we accept that they also have these wave-like properties. However, normally in the context of photons, we're trying to straddle the gap between both. And what it means is that photons can have wave-like properties like wavelength and frequency, but they're also treated like particles almost, particles with an energy. And the correct terminology really is we call them kind of particles with a discrete amount of energy. And this amount of energy can be calculated. We have this equation here where the energy of a photon is equal to Planck's constant, h, times by the frequency. Or we talked about it as a wave. We know that frequency can be equated to speed over wavelength. And therefore, we can just kind of rearrange this equation into hc over lambda. Again, where h is something called Planck's constant. So h is just always equal to this. Here, I've got a little task for you guys to do. I'd like you to calculate the energy carried by a photon with a wavelength of 400 nanometers. So 400 nanometers would correspond to kind of violet light end of the spectrum. And this is our visible spectrum. So this is kind of the range of human sight. We'll talk about this in a minute, but yeah, if you think you can give this a go, again, F is frequency, c is our speed of light, and lambda is the wavelength of a photon. If you think you can attempt to work this out, and then whack something in the chat or unmute when you think you've done it. How are we getting on, guys? That looks like a good answer. Can I offer any help to anybody? Is anybody struggling a little bit? Are you all happy with what a nanometer is? NM? Yeah, nicely done, guys. Well done. I don't want to rush anybody that's still going. If anybody is still going, please let me know. And then in kind of 10 seconds or so, we'll move on if not. Okay, we'll move on. Everybody that put an answer in, you got it right. Well done. That is exactly right. I think this is kind of more just kind of the higher up in physics that you go, the more you start to see constants like Planck's constant here, where they're kind of really horrible numbers with no, I mean, they do have an intuitive value, and their intuitive value is that they take these two physical values and they turn it into another physical value. But with the exception of the fact that they make the physics true, they have no real intuitive value. And so sometimes they're a bit of a pain to work with. But we have stuff like Planck's constant. We have stuff like the permeability of free space. We have stuff like kind of the gravitational constant that makes Newton's equations true. You might have encountered that already. And again, I mean, they do have a real meaning, and the real meaning is that with the kind of unit system we use, they make the maths true, they make the physics work. But other than that, they're just kind of horrible numbers, as you can see here, 6.63 times 10 to the negative 34. So yeah, but well done for everybody that used them. You all got them right, so well done. We don't need to go through that. So we've talked about what light is, and how we can kind of quantize the energy contained in certain light sources. And what you just worked out there was how much energy a photon in a violet light, a visible purple light, as you might see on the screen, contains. And that's really helpful for us as physicists because it opens up a whole host of kind of understanding, and suddenly we can start to look at electrons differently, and we can discover that actually electrons don't live in a secluded world of atoms. They very much interact with the world around them. This is your kind of classical model of an atom, and for the sake of this is kind of perfectly fine. And what we can see here is that you have your protons and your neutrons that make up the nucleus, and you have your orbiting electrons. But the big thing now, and the big thing with kind of the photoelectric effect, is that electrons can have different amounts of energy. And depending on it kind of one leads on to the other. It's a bit of a circular argument, I know, but depending on where they sit, what shell they're in, they have different amounts of energy, and vice versa. These two electrons here, the ones in the first orbital, they will have the same amount of energy. And this electron will have slightly more energy. And that's reflective of the fact that it sits in a higher energy shell. And the kind of energy order of the shells, for the sake of this, can be kind of simply taken as every time you go one shell further out, an electron will have slightly more energy. And it can be due to a lot of things. But the most common is the absorption of photons. And this is kind of how, in a lab setting and in the real world, we can promote electrons to higher energy shells. You can see this electron here orbiting the nucleus. When a photon comes in and it's absorbed by the electron, we see the electron move into an excited state. And this excited state is just a promotion from the first energy level to the second energy level, and it'll hang out here. It'll sit on this more excited state, and this is where we have to start to get into kind of the more technical stuff. I hope so far it's all made sense, and that's a kind of very conceptual understanding way of talking about it. But where it gets a bit more confusing is that these energy levels are what we call discrete. And it means electrons can't sit in between them. They have to lie on an energy level. So an electron can either be on the first energy level or the second energy level, but it can't be somewhere in between. It can't be on a 1.5 energy level. And so what this means is that when photons come in, if a photon, for simplicity's sake, let's say that energy level 1 has 10 electron volts of energy, which is quite a lot. Electron volts are an incredibly small amount of energy, like times 10 to the 30, times 10 to the negative 30-ish energy. But electron volts are the way in which we measure the energy of electrons. So we'll call this first ground state, is what we refer to the first state as. We call it the ground state. We'll call that 10 electron volts worth of energy. And we'll call this second one 20 electron volts. So first is 10, second is 20. If a photon comes in with an energy of 5 electron volts and it wants to hit the electron, do we think the electron's going to be allowed to take it? Where does this energy go? Okay, very good question. I'll cover that in just a second. Do we think the photon is allowed to hit the electron? Is the electron allowed to absorb this energy? Is it allowed to have 15 electron volts on the 10 shell or 15 electron volts in the 20 shell? The answer is no. An electron can't absorb a photon that doesn't correspond to yes, no is right, yeah. It can't do it because it has to sit on these, we call them discrete, and discrete is kind of quite an important word. Discrete energy levels. So what it means is that you'll see photons can only hit electrons with the corresponding energy. In this case, we've said that the ground state has 10 electron volts and the second has 20. So kind of 20 minus 10, the difference between them is 10 electron volts. And so these electrons for this atom, whatever it be, these electrons will only absorb photons with an energy of 10 electron volts. And this is a pretty big deal because it means that we can start to shine a kind of light spectrum, much like this, and we can say, well, you know, when we shine this spectrum, we're going to assume that some some wavelength of light will correspond to the energy difference between the first shell and the second shell, or two certain shells, and it means we can start to look at light spectrums and say which bit of the spectrum is missing. Because if we shone this spectrum here, and we found that at kind of 550 here, there was just a black line, that would be because all of the light has passed through, because none of that light corresponds to an energy difference between electron shells. And at 550, the atoms have absorbed the energy. They've absorbed the photons because they correspond to that exact jump between two energy levels. And you get an emission, you get a spectrum, which let me try and find a photo for you because they're really interesting. Absorption spectra. 1 moment. Someone asked a question earlier. Yes, it means they can only absorb photons that have an energy difference equal to the shell energy difference. Exactly right, Hansraj. And sorry, where does this energy, where is the energy go when electrons move to higher energy shells? So the answer is that the energy doesn't go anywhere. For them to move to higher energy shells, their energy must be increasing. And for their energy to increase, they must be gaining some energy. And the energy they gain is in the form of these absorption spectra, in this light they absorb. Oh, I found, let me, yeah, you can see, sorry. Cool. This is really blurry, but you can, let's see if we can find. So, and then we're going to kind of skip onwards a little bit, but here, can you see these black lines? Is there a way of me, can I open this, or is it going to be some dodgy website? Let's have a look. Apologies. This is the problem with physics is you can get sidetracked so easily talking about stuff. Right, so let's look at this for helium. So this would be our kind of 400 to 750 or whatever it be nanometer light spectra that we talked about earlier. And here we can see for helium, they've shone this full spectra of light at helium, and we've got these lines missing. See? And these missing lines correspond to different energy level jumps of the electrons. Different electrons are saying, well, for me to get promoted to the next higher state, I need light of 400 nanometers. I need an energy difference of, you guys worked it out just a minute ago, 4.97 times 10 to the negative 19 joules. And the different electrons in the different states are just seeing this full spectrum of light come through, and they're just picking the photons that correspond to the energy they need to gain. And so you just see these sharp cut-off lines in the spectrum. And each different line, you see how there's two groups closer together here, two closer together, three closer together. Each different line will be a different energy state. It'd be a slightly different energy level that they're absorbing. And I was going to talk about this slightly later, but we can talk about it now. How do we think the electrons go down energy levels? Because we can't always just promote them up and up and up. Otherwise, we'd kind of be getting to like an infinite energy state. They have to find a way to go back down energy levels. How do you think they might do that? They do. They release the excess energy. How do we think they might release this energy? How have we talked about them gaining energy? Everybody's on the right lines. They do need to lose some energy. Yeah, in the form of photons. So what we can see now is I've moved that up to somewhere where I can't grab it anymore. Let me get rid of that. They emit photons. In the same way they gain energy by absorbing photons, they lose energy by emitting them. And what we can now see here is the emission spectra, the energy that the electrons need to lose to go down one energy level. So look, this, you see where all the black lines are? They correspond exactly to where the kind of colorful lines are on the spectrum above. And that's because if we can see my mouse here, if this electron needs to absorb a certain amount of energy to move up into this next electron state, and if it absorbed this ray, this kind of ray of light, it would move up again. Well, it's absorbed this blue light to move up. And now if it wants to move down, it has to emit that light. It has to get rid of this same amount of energy, move back down to the previous state. And so this is actually how we image stars. We can work out the content of stars by looking at the emission spectra of, in the case of stars, mainly the gases, but sometimes the metals, of, for example, helium. We point our telescopes up at the sky and we see obviously all of the light. And you say, well, we can kind of break this light down into its composite colors. And its composite colors will correspond to all of the different emissions taking place. And we can do some really cool science where we start to say, okay, at 551 nanometers being a kind of green emission spectra, well, kind of only helium emits light at that wavelength. Obviously, this is a bit of an oversimplification because we have 180 something elements, maybe more actually. I think it might be over 200. And with 200 elements and they all emit, kind of look at this spectrum, it's got about 10 different emission lines on it. There's no way that every single emission line is going to be unique to that one element. You know, helium and uranium might share the same emission line, but we can kind of say what's more likely. If we know that the star is made up of hydrogen and some other thing, and it looks like it's flowing and it's moving and it looks almost gas-like in nature, the likelihood is that it's probably helium rather than uranium, right? And if we were to go through and say, well, let's look at all 10 emission spectra, this would be almost like a fingerprint of the gas. Only helium will have these 10 emission lines in these exact kind of to the nanometer wavelengths. How the formation of a rainbow is related to this. Yeah. So the rainbow is, do we still have that old photo open? Yeah. So here you can now see a prism being used to create a rainbow. And in the clouds, you often see rainbows happen when you kind of have sun and rain, right? And that's because rain has a different different refractive index to kind of the air, much like a prism has a different diffractive index to the air. And what happens is the light passes through these kind of rain droplets. And this is kind of more to do with optics now, but basically we go back to our light spectrum here. They have different wavelengths, right? We talked about this being, I'll go back to our slides actually, it might be. Oh. Got different wavelengths, 400 nanometers through to about 700 nanometers here. And these different wavelengths have different frequencies. And the different frequencies cause them to travel through mediums, in this case, objects with different refractive indexes at different speeds. And because they travel through at different speeds, they refract different amounts. So what happens is the red light is traveling, red light travels relatively, it has a lower frequency because it has a longer wavelength. And so the red light travels a different distance, it diffracts less than the purple light, which has a much higher frequency because it has a shorter wavelength. And it causes this kind of dispersion of light because white light is just the combination of all the colors of the rainbow. And it's a combination of all of the different emission spectra. And that's why, you know, if you use kind of filters on light, you can filter out all colors except red or except green or whatever it be. The rainbows form because this same science is happening up in the clouds. White light is hitting rain droplets and it's being separated based on the frequency of the light. And you see this kind of projected across the sky in these kind of beautiful rainbows. Now, what we're going to do, unless, I mean, kind of sorry, I don't want to rush on because we've just covered quite a lot there, kind of quite a lot of cool science. So if anybody wants to talk about anything there, just kind of send me a message. Otherwise, we will continue
Sir?
onwards. Yeah.
Could you please repeat that phenomena of light spectra and a short net?
Yes, light spectra emission, yeah. So the electrons in a certain atom need to lose a certain particular amount of energy to go from a higher state into a lower state. And this certain amount of energy corresponds to a certain frequency or a certain wavelength of light. Much like in this question, I basically told you had purple light, and I asked you to work out the energy of a photon of purple light. Well, they're almost doing the same question backwards. They're saying, I want to lose 8 times 10 to the negative 19 joules. What color light do I need to emit to lose that energy? And they're picking 550 nanometers. They're saying that's the wavelength of light that I need to emit to lose that particular amount of energy. And they're emitting that in the form of green light. But because they've got so many different energy levels, they kind of have essentially near infinite energy levels. They're emitting so many different colors. You know, one electron's saying red, one's saying yellow, one's saying green. And that's why you get this red, yellow, green, and the blues and the purples. And that's like a fingerprint for certain atoms, certain elements, sorry. So helium will always emit this spectrum. And, you know, let's see if we can find some other kind of spectrum and compare them. Here, look at this. So you can see they're all different. No two emission spectra are the same. Some of them might look a little bit similar. Helium and argon here look a little bit similar, but they're all totally different. And it means if you have a kind of high resolution enough measuring device, you can make a unique fingerprint for every atom, for every element, sorry. I keep saying atom. It's dependent on the element. So helium, oxygen, neon, argon, xenon. Happy?
Yes, sir.
Does the kind of, yeah? When and where these emissions of colors are seen? Is there an example other than the rainbow? So yeah, these kind of colors are seen in stars, and they are what help us gauge how old certain stars are, because we've talked about nuclear fusion, which is what stars do, right? They take helium and hydrogen and they push them together under huge temperatures and huge pressures, and they form more dense elements. They go kind of hydrogen, helium, and they go right the way up into kind of the most heavy elements that we see in the world around us today, because they've all come from stars. So the leads, the uraniums, the plutoniums, blah, they all come from stars. And a kind of real world example, kind of, it might feel more theoretical because obviously you or I can't see it, but these spectrums will have come from stars or from gases of just condensed gas of helium that's given lots of energy and then allowed to release this energy. And like I was saying, we can track the age of stars by saying, well, this star is emitting lots of hydrogen spectra. Have they got a hydrogen spectra? No, they've got stars emitting lots of hydrogen spectra. And it's only emitting kind of 10% helium and only kind of 3% of heavier elements. So this star must be quite young because it's not had the opportunity to fuse all of these atoms together. Whereas if we were saying, well, suddenly actually this star is only 30% hydrogen and it's 10% helium and the rest of it is all kind of heavy metals. Well, we know this star must be quite old because it would have taken millions and billions of years for it to fuse all of that hydrogen and fuse all of that helium and make these heavier elements. So we can gauge the age of stars based on the emission spectra they create. And actually, a little game for you. Have a look at this unknown gas spectrum here. We've got this from, say, imaging a star, and we're trying to work out what the kind of big component gas of it is. Obviously, this is probably more aimed at the emission spectra of an unknown gas in a laboratory rather than an unknown gas in a star. But kind of think to yourselves, maybe stick in the chat if you know, what gas might this be? What fingerprint does it look like here? Yes, neon, exactly. The reason I say it might not be a star is neon isn't a very common gas for us to find in stars. You might find a tiny bit of neon, but our most common ones are hydrogen and helium and the much lighter elements. Right. That's a kind of almost quite a cool digression, but if we move back to the slides, I've now got a question for you of where do you think some of the most common applications of the photoelectric effect are? And if I'll try and describe it, and you guys think about where it might get used. So in summary, the photoelectric effect is the ability for photons of light to hit electrons and to increase the energy of the electrons. Think about what electrons are used for in every day. What do electrons create for us? Think about where the different energies of light might be useful. There's lots of different uses. So I've got a couple in the slides after this, but if you can name any that I haven't got, you get extra credit. It's tough. So don't.
And tube lights.
Yes.
And
yeah, so
tube
that would
lights.
be, yeah, so that would be, it massively depends on the light. It could be photo emission. It could be the emission of photons based on electrons being excited and then looking to de-excite. That is potentially more likely to be actually tube lights are gas, aren't they? No, so you're right. You're right. I take it back. Tube lights are full of gas. Yeah, that's exactly right. Tube lights do that. Neon bulbs. In that case, neon bulbs, no, because what they do with bulbs is they have oh no.
So what
Sorry,
about
take it back
electron
again.
guns?
Electron what, sorry?
I said electron guns. There we also use emission of electrons for cathode ray oscilloscope.
Yes, yeah, it will be. Yeah, I mean, I'm not that familiar with them, but it sounds like it may well be. Yeah, kind of one of the examples I was thinking of was like neon signs, like the street signs you see that are kind of purple or bright red or green. They work with neon gas being excited, and then you get those kind of green emission. That's what causes the green light. Some of the other cool examples I've got are digital cameras. So what happens with a digital camera when we take a picture is photons are instant in this little kind of box, this screen. And this screen, when we get to the kind of, we're now talking about micrometers here. So this is tiny, tiny, tiny. You see these little black and brown dots, and these are individual pixels. And a photon will hit one of these pixels, and the pixel will do the exact same math that you did before. It will say, it will absorb the photon, and it will say, how much energy did that photon have? and that energy will correspond to the color of the light that hit that photon. And then it will build all of these individual kind of pixel by pixel colors into a picture. And that picture will be displayed probably on a bunch of pixels, like a TV screen or the kind of screen of a digital camera. But that's all built up of the individual pixels doing the same maths that you guys did earlier, where they try and work out what color light hit it based on the energy that's absorbed. Another example, and this is one I potentially you might feel more obvious once I show it to you. Solar panels. Solar panels work on the basis of photons of light hitting solar panels. Solar panels absorb the light. They excite electrons. These electrons then create a current in the form of electricity. And that electricity is used to power a kind of national grid, or, TVs, kettles, whatever it be. So this is one of the kind of more up and coming.
Sir,
Yeah.
can we discuss how these solar panels generate electricity from photons?
We can try. I must admit, I'm not an absolute solar panel wizard. But let me. Let me have a little look in my notes and we'll see what I can do. At a deeper level, beyond kind of photons hitting these kind of photovoltaic cells, which is just like the kind of components that you can maybe see here, and those taking the energy and turning it into higher energy electrons. The electrons are absorbing the light. I don't really know, is the truth. And I can try and have a little bit of a look, and I can send it to the group chat for you, or I can talk about it next time. But I must admit, off the top of my head, I don't know how solar panels work. This is kind of a niche that I'm not an expert on. But yeah, we'll talk about that. I'll put that in the notes, and we'll talk about that next time. Has anybody else got any questions? Hopefully that I can answer. But fire away. Don't be kind to me. Let's just see what happens. No questions about this? Oh, got one. Yes. Ayan, I saw your suggestions on the group chat, and I was going to address it at the start of the lesson, but I wasn't sure if you were in yet. If you want me to talk about stuff in the lesson, I kind of need you to send it like a day or two in advance at least, because of the time difference. I kind of do these as soon as I wake up, so I don't really have time to do to like change the slides and add stuff in once it's kind of before a day's kind of notice. So what I will do is I will make sure that your stuff is in the kind of content for next lesson. But I'm afraid I can't talk about it this lesson because I just haven't had the time to kind of prepare it. I hope that makes sense. What I can do now, though. Sure. Awesome. Cool. Thank you. What I'll do now, though, is the stuff that you guys asked me to talk about this lesson at the end of last lesson. I will talk about now. So you asked about pulsars and about black holes. So what are pulsars? Pulsars are highly magnetized neutron stars that spin around in circles rapidly, and they emit kind of beams of electromagnetic radiation from their poles. And these beams are predominantly made up of radio waves, but they will contain other forms of electromagnetic radiation. EM radiation being, microwaves, radio waves, X-rays, and all other types of kind of radiation that you'll have learned about. And the reason we call them pulsars is because they seem to pulse. They look almost like a lighthouse to us. And that's because you can only see them when this beam is pointed directly at you. So in this case, directly at Earth. And so what it does is it spins around and it seems to pulse in the sky because we'll only ever see it when it's pointing at us, and it spins in a very kind of regular fashion. So I've got a little video for you. I hope you guys are gonna be able to see this, and it's not. Oh, go back to the stars. Don't care about that. Mute. So, come on. Look, can you see how they spin? When it comes across the camera, it almost pulse. And that's what we see. That's how we see them. When it's away from us, we can't even see them. And how do they form? Well, they form in the same way as a neutron star. They form when small to medium stars die and they kind of collapse in on themselves, and they become this very dense cluster of radiation and mass. And the thing that separates a pulsar from a normal neutron star is that it spins, and it spins so rapidly that it begins to kind of emit this radiation from its poles and have that kind of pulsing motion that is kind of unique to a pulsar. Do the beams of pulsars that contain radio waves cut off the rocks or stars in space? I haven't heard of it doing so. I mean, it's not infeasible to think it might. Truth is, I actually don't know if we know as a scientific community, because that'd be such a it'd be such a localized phenomena where you'll only see that happening really close to the star. But the radio waves might kind of the radiation and the radio waves might ionize some of the elements within a rock, and that might cause them to become unstable and potentially to kind of break apart. But I don't know if I don't think it's like a kind of high-tech laser or like a really, really powerful laser where if you were to shine that through a rock, it would just cut it in half. I don't think it's quite like that. I hope that's kind of answered your question. Any questions about pulsars? I'll move on to black holes, and just fire away as and when you think of questions. So black holes form on the death of much, much larger stars. And when these bigger stars die, they turn into supernova. And these supernova are basically just huge explosions. The reason this happens is because they're so large and they're so unstable that they kind of can't just condense down into a kind of hot mass like a neutron star, which you can see here. They explode, and when they explode, they can kind of begin to spin, and this spinning motion, in a way similar to a pulsar, but slightly different. Spinning motion combined with the kind of huge mass of the star will begin to suck in other bits of kind of mass that surround the star, much like a kind of what do you call them? Let's see, kind of tornado or a kind of hurricane will spin and it will pull in kind of more air and material and it will grow. What if a pulsar formed close to Earth? So if a pulsar formed close to Earth, it could potentially be dangerous. it could be dangerous in many aspects because, I mean, if we start from the beginning of a pulsar, how does it form? Well, it forms when a star dies. So the closest star to Earth would obviously be our sun. If our sun died, probably the pulsar is probably the least of our issues once the sun's died. But if a pulsar formed kind of at the next nearest star, which is probably a few kind of, I think it might be a few thousand light years away, then, so what are your perspectives about how the Earth encountered the situation? Yeah, so I think once you say that it's not going to be the sun, because you kind of if it is the sun, that's the least of your issues. I think your biggest issue would be the amount of radiation that it releases. And like you say, I don't think it would potentially cut the Earth in half, but I think what it might do is it might make it almost inhabitable because you would receive such a huge amount of ionizing radiation like X-rays and gamma rays and kind of radio waves, microwaves, etc., that it probably wouldn't be conducive to life. We use X-rays and gamma rays to disinfect medical equipment. If you go into a hospital, one of the most common ways of disinfecting kind of scalpels and other surgical instruments from bacteria is to shine intense electromagnetic radiation on it. And this radiation kills bacteria and it kills cells. Well, if you imagine this on almost a cosmic scale with a pulsar shining huge amounts of electromagnetic radiation on Earth, it would probably have the same effect on us. It would probably kill cells. So that would be us, that would be all the animals, that would be trees and fungi and all the plants and stuff. So all in all, I think it wouldn't be very good for Earth if a pulsar formed on our doorstep. Again, I hope that answers the question. Keep firing away with questions. It's cool to talk about this stuff. And then, yeah, like we said earlier, smaller stars will form into neutron stars. I've now got I'll just play you. Yes, get this verification, whatever that is. I've now got a little video to play you of how black holes form. Hopefully we don't have to watch any adverts. Let me know, by the way, if oh, sorry, I've got a question. How will a pulsar end? Right. A pulsar will end most likely because it's kind of emitted so much of its energy in the form of radiation that it can just no longer it can no longer begin to emit such huge amounts of radiation. But that'll obviously take a huge period of time because they're such high energy objects. And then once it's done that, once it's either kind of its spin has slowed down and it's stopped emitting radiation, it may just turn into a neutron star and live out its life as a neutron star. Or feasibly, if it kind of absorbed enough kind of other mass and got hit by enough meteors and stuff to keep it spinning, maybe it could just go on forever. It's hugely dependent on the circumstances. Right, here we go. This is how a black hole forms. So we see these two these will be very massive stars, like much bigger than the sun, potentially hundreds of times bigger than the sun. We'll see them kind of begin to orbit one another, but in an unstable orbit, and they kind of collapse upon themselves, and they begin to merge into one spinning supermassive object. And this spinning supermassive object will will then begin to suck in more mass, and it begin to form a kind of characteristic black hole, much like we can see from our photo here. The difference here is that everything inside this kind of event horizon is what we call this black ring around the edge. There is so much gravity that light can't escape. And because the light can't escape, we can't actually see what's happening. Yeah, and that's the end of today's session. If you've got any questions, fire away. We've slightly overrun, but any quick questions I'll kind of attempt to answer, and any that we can't answer now, I'll address either in the group chat or at the start of next session, depending on how much I think we need to kind of go over with them. And Ion, for your questions of the weightlessness of satellites and gravity-free systems, as well as artificial gravity, we will go over that next time. Make sure that's the first thing we do next time.
Sir, could you please explain what pulsar is? Because I got disconnected when you were describing it.
Yes, yeah, I will. The black holes have as much gravitational force as it can full of the Earth even. Yeah, so black holes have way more gravity than the Earth. Gravity is proportional to the mass of an object, and the mass of a black hole will be thousands of times stronger than the mass of the Earth. Our own sun is thousands of times stronger, thousands of times more massive than the Earth, and that is nowhere near heavy enough to become a black hole. So the gravitational force in a black hole would be, depending on where in the black hole you were, kind of almost infinitely more powerful than the gravitational force of the Earth. These things are almost kind of uncomprehendibly strong gravity. So yeah, much, much, much greater than the Earth. And then Hansraj, in terms of pulsars, pulsars are the kind of neutron stars that are formed from smaller stars. Neutron stars form from the death of a smaller star. And it's neutron stars that are spinning rapidly. And this rapid spinning motion kind of causes them to emit huge amounts of electromagnetic radiation from their poles. And this radiation is predominantly in the form of radio waves, but other types of radiation too, like X-rays and gamma rays. And a pulsar is much like a lighthouse. You can only actually see it. This one's from side on, but you can only actually see it when these poles are pointed at you. These are kind of artistic representations of what we think they might look like. These aren't real photos or images. A real image would just be that dot flashing on and off, and that would represent this swinging into motion, swinging away, you swinging in again. You can see it. So it'd be like on, off, 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 on, off, 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 on, and we can measure kind of the rate of spin based on how quickly we see that flashing light and that pulsing light, hence why it's called a pulsar. Where does the energy go when anything is absorbed into a black hole? The answer is we don't know. Black holes are this point where we call them a singularity because they're so extreme and they have such extreme values. We don't really understand, and we don't at the moment have a way of measuring them in terms of the science that goes on within a black hole. We can look at what happens around them, but in a way, a good way to visualize the science of a black hole is the same way we see the photos of the black hole, which is everything around the black hole we can understand, but once we get inside this event horizon, all we know is that the gravity and the mass is so huge that everything that goes in doesn't come back out. but what actually happens there, we don't know. It's yeah, it's kind of like the next frontier of physics, if you like, the research of black holes.
Sir,
Yeah.
according to the law of conservation of energy, can we say that the energy might be getting stored in this because it cannot be destroyed?
Yes. I think that's a very logical thing to say. It's just tough to know because obviously our understanding of physics isn't complete. It's a kind of growing field where we continue to learn year upon year, and discovery upon discovery. And so our current understanding is that energy cannot be created or destroyed. And I think that is correct. But potentially black holes could be creating dark energy, dark matter, which again is a content for a whole nother lesson. I know by saying those things, I've opened up a can of worms, and you guys are going to be desperate to know what I'm talking about. In summary, it's energy and matter that we know must exist, but we can't see. And I'm going to have to talk about that next time because that will take a great amount of time to talk about. But I think it's reasonable to say that this energy must be getting stored somewhere. Where or how, we don't know. That's why they're so interesting.
And so it is also possible that it makes the theory of conservation of energy incorrect.
It's possible. It's probably very unlikely because we've now begun to make some very big discoveries based on our understanding of the conservation of energy. You know, we've found subatomic particles that we didn't think existed, in the form of neutrinos, which are just kind of little bits of radiation and energy that are released when certain kind of particle collisions happen. But it's not impossible that it's wrong. I'd just say it's highly unlikely because we're still proving some of the kind of greatest physicists wrong on a kind of, well, I was going to say daily basis, not a daily basis, but we kind of make these sweeping statements like Newton with gravity, and then we have to rethink these statements as Einstein develops relativity, and so we just have to kind of build on what we know from the discoveries we've made. I would say it's unlikely that conservation of energy is wrong, but we can't say for certain that it's correct. Kind of the beauty of physics. Any other questions? Okay. Oh, one last question, then more. No, sir. Okay. Okay. Perfect. In which case, thank you very much, guys. It's been a pleasure to teach you as always. And if you have any questions, Ian, I'll address your stuff at the start of next lecture. I will talk a little bit about dark matter then, dark energy, and attempt to kind of relate this to black holes and what might happen. And we'll also talk about how solar panels create energy on a kind of deeper level beyond kind of photo emission and so on. In which case, I will stop the recording and I will see you guys next time.